Okay, guys, today we're looking, and for me it's the same day, at momentum. So we found what the expectation value of position is, and now we have to talk about momentum. And I've also written in the last episode these three things on my whiteboard, and we didn't use them, but today we'll use them. So we have to find a way to get the expectation value of momentum. And how can we do it? Well, we have to get back to the origins of quantum mechanics. So, and we're also going to motivate what I was talking about in the first video, the Schrödinger equation. So what physicists do is to guess at a theory, then make predictions with that theory, and just find what the theory predicts about the universe, and then do experiments to see whether those predictions are true or not, and if the theory works or not. So we first need to guess. And this is our guess. So De Broglie proposed that if those relations were true for light, why aren't they also true for matter particles? And these are the relations. We have momentum equals h over lambda, where h is Planck constant. It was known to work for light, but not for matter particle. And the other relation is regarding the energy. Energy equals h, the same Planck's constant, times the frequency of light, of course. Now, this is not how physicists are to write these quantities. Physicists normally use this notation, h bar times k, and E equals h bar times omega. And why do they use this notation? Because this h bar is h divided by 2 pi, and it's more comfortable because it occurs a lot of times. Writing h bar is better rather than h. And k is called the wave number. It's not 1 over the wavelength, it's 2 pi over the wavelength, so a kind of angular wave number. And the same goes for the energy. This is the angular frequency, and this is h divided by 2 pi. So basically what happened is that Schrödinger was challenged to find an equation, a wave equation, because if light can behave as particles, why can't matter behave as waves? So he had to find an equation, and in order to find an equation, you have to start with something that is a wave. So he wrote this wave. He didn't know what psi the wave was. Then we understood that it could be interpreted as this probabilistic interpretation, in probabilistic wave. And it started with this plane wave. We're talking about one dimension here, by the way. So this is kx minus omega t. So this is a plane wave, sinusoidal wave, and well, if this is something, a wave regarding the quantities k and omega, then it has to satisfy an equation, and he wanted to find this equation. So this, of course, doesn't actually represent a real particle, but we're guessing as a theory, so not everything should make perfectly sense because we're guessing. So he noticed the following thing. Well, if you take a derivative with respect to time of this quantity, look at what happens. You get a minus omega in front I omega, and then you get the same function. This is how exponential works. You take the derivative and you get the exponent to the front. And we can do also the same with respect to space. So this derivative, we bring this factor ik in front of it, and that's our relation. Now, as you can see, we can sort of recover from the wave function this momentum and the energy. And well, how can we do it? If we have, what we're interested in is finding the energy of a system, and the energy of a system, it's given by its Hamiltonian, and the Hamiltonian is potential plus kinetic energy, so kinetic energy, p squared over 2m plus v. So, as you can see, we need to find p in some way. Well, we find in the last video that x, well, we'll see it in this video. Don't consider the potential for now. We have to focus on the energy, Hamiltonian, and the momentum. Okay, so we want to kind of get our quantities times psi, and here we have, let's consider the energy first. We have an omega here and an omega here. So if we kind of divide by minus I, well, if we multiply by minus 1 over I, and then we multiply by h bar, and we take this derivative with respect to time of our wave function, well, we found that we get this when we take the derivative. But if we multiply by this factor, we basically get our energy, because we get h bar omega. So this is a way to recover the energy from our wave function. And there's also a way to recover momentum from this special derivative. Same trick, we divide by I and we multiply by h bar. And we take the derivative, of course, of psi, and this gives us h bar k, so p times psi. Now, we just found that from we can recover the momentum and the energy from this wave by doing this weird operation. So we might define the momentum operator, something that acts on the function to give me momentum, as, well, we have 1 over I, so we can put minus I, same thing, h bar d over dx. And this equation doesn't make sense on its own, because we need to apply it to a function to actually make sense of it. This is a differential operator, and we can do the same thing with energy, because the energy operator, this is an at, just to identify operators. And we have 1 over I, so we can bring I in the numerator and change the sign. So we have I h bar d by dt. And as you can see, the Schrödinger equation, this is also the Hamiltonian operator, comes from, this is just guessing, so it's not a derivation, comes from trying to write an equation of a matter particle in terms of E and P, with this substitution, canonical substitution here, and this substitution we get using this equation to the Schrödinger equation. Now, all of this is to say that we kind of postulate that momentum, the momentum operator, whatever it means, is this quantity here. Remember, this is not a derivation, we just find that this works perfectly fine, and that's cool. We can describe the world using this fact here. Now, I don't know this story well, but I think Heisenberg got to this relation in another wave, and several physicists got this relation. But why do we care about this momentum operator? Well, when you apply the momentum operator on the previous psi, we found that you basically get the momentum times psi. And I think it's too early to talk about this. This is an eigen value of this eigenfunction, this kind of abstract linear algebra equation, and it basically tells the momentum the particle has if it is in that state psi. But a particle might be in a superposition of all these states, and the momentum also might be in this is also in a superposition of states. So we have a lot of different momentum we can find for that particle. Just by doing experiments, we will find, okay, this is the value I got. Now, this is important because we can go on and find, as we've done with position, the expectation value of P. And there is a theorem, I'm not going right now through all of this. This is called the, I don't remember the name, and it states that in quantum mechanics, the average values behaves like the quantities in classical mechanics. So in classical mechanics, we have P equals m times v, that is dx by dt. And in quantum mechanics, the same holds for expectation values, average values, rather than the definite values themselves. And we can find this according to this fact. I'm not going through that. You can check a lot of textbooks like Griffiths, and you'll see that to find the expectation value of momentum, all you have to do is to take psi star times, or at least you sandwich the momentum operator between psi star and psi. What does this mean? Psi acts on psi, and you multiply by its conjugate. And we found in the previous video that the expectation value of x is similar. It's x times the probability density. And probability density is the same as psi star times psi. So we can write all of these as psi star times x times psi. And they're very similar. So when we find expectation values of things, we sandwich the operator representing that quantity between psi star and psi. Obviously, what is the x operator? Well, it's just the normal x. So we multiply by x whenever we talk about position operator. And we don't talk about position operator because of this fact, but we talk about momentum operator. And this is also why the potential is our well-behaved classical potential, because it is a function of x, and it might be a function of t. But a function of x it's just multiplying by x, so we don't need to go through the canonical substitution, weird substitution like this. And this turns out to work. In the next video, we're going to simplify this equation for a time-independent potential, and we'll start solving some simple systems. And I'll see you in the next video. Thanks for watching, and don't forget to subscribe to my channel. Bye.